Welcome to a new lesson of the Haskell course. This one is about how to handle errors in Haskell. Haskell is a compiled language, so we can subdivide all possible errors into compile time errors and runtime errors. Compile time errors are awesome. We love compile time errors because that means our program had something wrong in it and our compiler found it and reported to us before it reached to the end user. At the end of the day, the most important thing is that our users enjoy our software and don't encounter runtime errors. Because runtime errors are the worst. These errors happen while running the program, and they can and do happen to end users. Users that then get angry and stop paying and give us a 1-star review. Compared to most other programming languages, Haskell is exceptionally good at avoiding runtime errors, to the point that many say the phrase, "in Haskell, if it compiles, it works." This is thanks in large part to its powerful effect and type systems that can catch those errors at compile time, essentially moving many errors from runtime to compile time. Although, this doesn't mean we can forget about runtime errors. As we said in previous lessons, even if we were able to write perfect code, which we cannot, we are still running in the real world, where computers run out of memory, files that should exist don't, internet connections fail, etc. And on top of that, users do unimaginable things with our software. So, in this lesson, we will learn both how to handle runtime errors and how to use the type system to move some of those errors to compile time so we can catch them with the compiler's assistance. More specifically, we'll start by understanding what are exceptions. Then we are going to speedrun through the exception mechanism to know how to handle them at runtime. Then we will learn about optional values, maybe and either. Then we're going to see how we can move errors from one system to the other, from exceptions to optional values, and vice versa. At the end, we're going to learn about the trade-offs of the two systems and when you should use each one of them. Let's get started. Let's write a simple program to calculate the velocity of an object based on a number written in a file and the input of a person. For example, this one. In this program, we read a file, the distance traveled by an object, and then ask the user to provide a number, the time it took, using I/O actions. Then, once we get both values, we use the read function to parse them into int values and apply the div function to get the velocity of an object. In the end, we print back the velocity and a thank you message. This is a pretty simple program. It compiles. And if we have a file called anumber.txt with a number in it and the user provides a valid number, it works. Sadly, the real world is messy, and unexpected things can and do happen. When something unexpected happens, that's when we get an exception. For example, here are a few, but not all, the possible exceptions that the program could throw at us. If there's no file called anumber.txt, we get an exception when opening the file. The exception says right here, the file does not exist. And if there is a file but doesn't contain a number or the user inputs the wrong string, the read function will throw an exception because it couldn't parse the string into an int. And finally, if there is a number and both are numbers, so the read function correctly parses both values, we still could have the time value being a 0, causing a divide by 0 exception. Currently, all these exceptions cause our program to halt. But of course, a robust program should not collapse if something unexpected happens. Luckily, we have a couple of ways to handle these exceptions. Handling exceptions in Haskell is not a small subject. Haskell has its own exception mechanism, and you can go crazy creating your own hierarchical error structures using alternative libraries, etc. But you have more important things to learn before that. So, in this lesson, we're going to speed run the subjects in a way that you'll have an overall idea of how it works and you'll be able to handle common runtime errors. Okay, let's say we want to build an AI for a self-driving car. AI is all the rage right now, so we're going to build a prototype to get some VC funding and improve it later. To simplify the problem, we will start with a car that can only go straight and react to traffic lights. Something like this. In these complex cases, it's usual to have several different sensors, systems, and predictive models. But because no one invested in our AI yet, we don't have the money to spend on a sensor. So we'll be the sensor. We will sit inside the car and type the color of the traffic light. So the program first will ask us for the color of the traffic light. We will pass the color to the next move function that will predict what to do next, and we will print back whatever the next move function provides. Once we have our next move, we recursively call the dump AI car action so we can input the next traffic light. This next move function eventually should send a signal to the gas and brakes. For now, it just prints the next move on the screen. Now, let's create the next move function. We are taking a string that represents the color of traffic lights. So we could do something like this. Here we create a new data type called traffic lights that could be either red, yellow, or green. So then when we take the color of type string, we can read color, and then if the traffic light is red, we're going to stop. If the traffic light is yellow, we're going to wait. And if the traffic light is green, we're going to go. This is technically right, but we have two problems. If we write something different than any of those three constructors, our program halts, and subsequently the car crashes with us inside. And the other problem is that the error provided in the case it fails doesn't provide much actionable information. Take into account that we might be parsing several signals in several different places, so not being able to parse might not be enough to know where is the problem. Let's solve this second issue first by providing a more expressive exception. To create our own exception, we just need to create a good old data type and make it an instance of the exception type class. So let's create a data type that represents the possible failures. We will call the type traffic lights exception, and the possible constructors are traffic light is off, and we have the wrong color. The wrong color takes a string so we can show in the exception what was the value we couldn't parse. Now, so far, values of type traffic light exceptions are what we call normal values. To make them exceptional, we have to first import the control.exception module and make the type an instance of the exception type class, like this. Notice we don't define the behaviors with the where keyword. That's because we don't have to. All the behaviors of the exception type class have default implementations. So we only need to indicate that the traffic light exception type can use those. This conveniently allows us to use exception values without entering into how the exception type class is defined and the nitty-gritty of the mechanism. things that will take too long to properly go over, and will touch subjects that are a bit outside of the beginner's scope. So yeah, that's all we need to do. With that single line of code, we transform our normal type into an exceptional type. That means we can throw and catch values of type traffic light exception like any other built-in exception. But what does that mean exactly? Throwing exceptions means halting the current program's execution and sending a signal with some information about what went wrong. That signal is the exception. We have a couple of options to throw exceptions. We're going to go with throwIO. As the name suggests, throwIO gets a type that is an instance of the exception type class and throws an exception within the IO context. We return a value within the impure IO context because exceptions can have side effects. Technically, you can throw exceptions from pure code using a function called throw without the IO, but it's highly recommended to use throwIO to maintain our pure code exception free. Okay, now that we have throwIO, let's change the next move function to manually parse the string instead of using the read function and throw as many exceptions as we want. And here's where we encounter one of the downsides of throwing exception. We don't want to throw from pure code because due to laziness it's hard to predict, so we throw from the IO context. This means our previously pure next move function is now impure, and we lose all the advantages that come with purity. We'll talk more about this at the end of the lecture. In this case, we don't read the color, we don't try to parse it into another type, we just pattern match the string value to red, and in this case we return stop, yellow we return wait, green we return go, so far same as before. But now, if the color is black, it means that the traffic light is off, something that should not happen, so we throw the exception of value traffic light is off. And on top of that, we use a wildcard to pattern match for any other value, and we throw the exception wrong color, providing the actual value we tried to use with a helpful message. So, if we apply next move to one of the two final patterns, instead of returning a value, we throw an exception. If we provide black, we throw the traffic lights of exception. If we provide any other thing, rainbow, for example, we return the wrong color exception. Rainbow is not a valid color. This solves the issue of not providing enough information because we can add custom messages that help when debugging our program. Keep in mind that this function can be buried inside a massive program, but because the exception is so specific, we instantly know what's wrong and where we should go to fix it. But if we leave it like this, we just created a fancier way for our program to halt. To make our program more resilient, we're going to catch, handle, and recover from this exception. Same as with throwIO, there are several ways to catch and handle an exception. One of them is using the catch function. As you can see, this function takes two parameters, a computation to run, and a function that takes a value that is an instance of the exception type class and returns an IO action of the same type as the computation we want to run. So we always return the value of type IOA. The catch function executes the IO action we provide as the first parameter. If everything goes well, it returns the result and that's it. But if some exception arises, it catches it and gives it to the handling function we provide as second argument. In that handling function, we can write all sorts of code to address these exceptions and resume our program. For example, we can use catch to handle our traffic light exception like this. The first part of the action is the same as before. We ask for a traffic light, we get the color, we get a response, print the next step, and recursively run the same function. But the key difference is that the next move color now has a catch and a handler. The catch function takes the action we want to run, next move, applied to color, and if everything goes well, just returns that result. And if this next move applied to color throws an exception, the catch function will provide it to the handler that should try to recover from it. So now we need to define this handler. We define it here. The handler takes a value of type traffic light exception and returns a value of IO string. It takes the exceptions and we can do whatever we want. This is very important. We can write arbitrary logic to recover from this. We can create files, remove files, talk to databases, whatever. In our case, first we're going to print a put string line saying, hey, warning, this error happened. And then we do a case analysis. In the case that traffic light is off, we tell the car to proceed with caution. But if we have a wrong color, we don't care really about what was provided as value, but we know that something is wrong with our sensor, so we're going to gently stop the car and shut down the AI. Now, with this modification, it doesn't matter if the string isn't a valid color. The next move function will raise an exception, and because the exception is of type traffic light exception, the dumb AI car action will be able to catch it and give it to the handler to recover from it. In this case, if the traffic light is off, the car will proceed with caution. And if we happen to encounter any other color, that means something is wrong with the sensor. But instead of halting the program and leaving a moving car without a driver, the program continues the execution and gently stops the car. This is a brief interaction with the dumb AI car action. If we provide red, it will stop, green, it will go. Notice that every time we provide a correct value, it keeps going, asking the next traffic light, so the actual program doesn't halt, it keeps going. If we provide black, we print this warning, we catch the exception, we return a new value, proceed with caution, and the program keeps going, doesn't halt. Then rainbow, the same, the program keeps going and keeps going and keeps going. Now, at least, we won't crash if something's wrong with the sensor. If the exception is of any other type, it will keep propagating up the stack looking for a catch that can handle that specific type. If it doesn't find any, the program won't be able to recover. That's the end of our speedrun. There are a ton of things we didn't cover, but everything revolves around this notion of throwing and catching. If you can foresee an exception and know what the program should do in that case, you can implement a handler to recover from it. And how do we know the usual exceptions we could encounter? Look no further than in the same control.exception module from where we imported the exception type class. For example, if you are dealing with numeric operations, you can take a look at the arith exception data type. If you know what to do in those contexts, all you have to do is provide a catch that catches all values of type arith exception and then provide a way to handle them, either one by one or all the values the same way. Notice that divide by 0 is inside this arith exception type. And if we're dealing with arrays, you might encounter an exception of type array exception. This one is smaller, it's just two possible values, index out of bound and undefined element. And there are other types to handle different exceptions. In all those cases, all you have to do is catch the exception of a specific type and provide a handler function to recover from it. There may be no sensible way to continue. In those cases, we want to shut down gracefully. By shutting down gracefully, I mean cleaning up any open connections, killing orphan processes, writing some logs, etc. It depends on what you're doing. Now, the exception mechanism is great, but there's also a more straightforward and idiomatic way of handling errors, and that is using optional values. In Haskell and other functional programming languages, we have this notion of optional values. Those are values representing the possibility that a function may or may not return a meaningful value. In Haskell, optional values are represented by the maybe type. As you can see, it's a simple type. It has one nullary constructor, a constructor that doesn't have any parameters, and one constructor with a polymorphic value. The major implementation difference with the other way to handle exceptions is that maybe is a normal type. It's not special in any way other than what we, the developers, interpret by it. So, the critical thing to remember is how to interpret the maybe type when we encounter it. The maybe type represents a value that might or may not be there. So, when you see something like this, we read it as some function takes an int and a string and maybe returns a value. That's it. Now let's see it in practice. One common example is to show how we can safely divide by zero. In our regular day-to-day math, dividing by zero doesn't make any mathematical sense, when programming is the same. So, if we divide by zero using the div function like this, our program throws an exception. Let's solve this without using the exception mechanism. One of the first things we can think to resolve this issue is to create a function that handles this specific case separately, sort of like this. This saveDiv function takes two values that are instances of the integral type class, the one that provides the div behavior, and returns a value of the same type. In the first case, we pattern match to handle the case when the denominator is 0. And in the second, all other cases. The second case is easy. We know that y is not 0, so we can just use div with full confidence. But how should we handle the first case? There is no number that we could return that correctly represents this situation. Here's when the maybe type shines. Using maybe, we can modify our function to have the option of not returning a value at all. If there's no sensible value to be returned, we return a nothing. If there is, we can just divide, but because we have to return a value of type maybe a, we have to wrap the result with the just constructor. Notice that by avoiding the possibility of dividing by 0 from the get-go, we bypass the exception altogether. No need to handle exceptions if they never happen. The price that we have to pay is that the value now is wrapped by a constructor. So we have to unwrap it before using it. Now let's use the saveDiv function in a program. To do that, we will keep with the speed theme and create a program that takes the distance traveled by an object and the time it took as inputs, and it returns the velocity. As you can see, we asked for the first value and save it here. We asked for the second value, save it here. And then we use the read function to parse the two strings into numbers and apply the saveDiv function to both of them. If the time is not 0, we calculate the value and return just the velocity, and we can print the velocity value to the console. But if the time is 0, we return nothing. And in this case, we can print, hey, the time cannot be 0 and recursively call main. Now, if the person provides a 0 for the time, it will keep running and asking for the numbers again until it gives a valid time. By using this technique, we completely avoided a runtime error. It doesn't matter which numbers the user chooses, our program won't crash. But wait, what if the user doesn't write valid numbers as input? What if the user writes letters or symbols instead of numbers? In that case, the read function will be able to parse the string, and you guessed it, our program halted. Worry not, we have a solution. But before that, I'm going to extract some functions so the code fits in the slides. I'm going to extract the function to calculate the velocity. So it will take the distance, the time, and it will do distance, safe divide time to get the velocity safely. And on top of that, I'm going to extract all the actions to get the values, because those are the same always. So we ask for the first value, we run the action to get it, ask for the second, run the action to get it, and at the end we return a tuple with the distance and the time. So this is the get data action. And now by extracting all this code, our main function looks like this. We run the get data action to get the distance and the value of type string, and then we read those two values to parse them to ints and apply the velocity function to get the final velocity or the nothing. Much cleaner. Okay, so now let's proceed with the solution. We would like a read function that can avoid returning a meaningful value if it's unable to parse the string provided as parameter. Lucky for us, a function like that already comes with our base library, and it's inside the text.read module. The read maybe function takes a string and returns a maybe A when the type A has to be an instance of the read type class. So for example, if we apply read maybe to 57 string and we say that we want a return value of maybe integer, we get just 57. But if we try to apply read maybe to a value that doesn't match the type we want as result, we get nothing. So by using read maybe instead of read, we avoid all runtime errors due to a bad user input. If we replace read by read maybe, the main function is pretty much the same. We just change here this line to read maybe, but we do have an issue now. The velocity function takes two ints and returns a maybe int. But we are passing two maybes, so we have to change the velocity function like this. We start by changing the types. It takes a maybe int and maybe int and returns a maybe int. And now we have to pattern match for all the possible cases. But we only care about just one case, the case when both values were correctly parsed, so they are just values instead of nothing, because that's the only case when we can pass both values to the savedid function and get a result. If just one of these or both is nothing, we have no way of doing this safe division, so we are forced to return nothing. That's why here we have catch all values. There are many predefined functions that use the maybe type, both in the standard libraries and in libraries made by other developers. When you encounter them, you can use them all in the same way. Pattern match, handle both cases, and you're good to go. Optional values have a ton of benefits. You can handle the absence of value, because it provides a type-safe way to indicate the absence of a value, preventing many forms of runtime error. Also, using maybe forces you to explicitly handle both cases, when you have a value and when you don't, ensuring you address all possibilities and write more robust code. Also, optional values allow the developer to express uncertainty in a way that the consumer of the function is aware and can handle without the need to know how the function is implemented. If I see that a function returns a maybe, I don't need to know how it works, I just know that there exists a possibility that it will not provide the desired value, so I have to handle that case accordingly. And finally, you can compose optional values, as we did in the previous examples. We provided the output of the read maybe as input to velocity that use savediv inside. If something were run at any time, the nothing value will propagate throughout the function tree. Now, the maybe data type is not the only one in town that we can use to handle possibly problematic values. One downside of using maybe is that when we have several layers of optional values, we don't know what went wrong. In the previous code, for example, if we got a nothing at the end, what failed? The parsing of the first value, the parsing of the second value, the division by 0? We have no way to find out. Enter the either data type. The either data type is also pretty simple. The either type represents values with two possibilities. A value of type either AB is either left A or right B. You cannot have both. This is not necessarily related to error handling or optional values. Either can be used in many scenarios to interpret a binary choice. However, in the context of error handling, you can think of either as something that builds on top of maybe to provide a way to log what went wrong. The way we use either to handle errors is not forcing code, but by convention. The community overall uses the left constructor to hold an error value and the right constructor to hold a correct value. Based on the mnemonic, that right also means correct. So, now that we know about either, let's modify savediv to let us know if we tried to divide by 0. We can define savediv e that takes two values that have to be an instance of integral to be able to use the div function, and returns either a string or a value of the same type as the inputs. If we try to divide by 0, we return left. Hey, you cannot divide by 0, you fool. But if y is not 0, we can just apply div to both values and wrap it in the right constructor. Left always returns a string, right always returns the value we wanted. We chose string as the type for left so we can leave messages to the user or developer. Although using a string to leave a message is the intuitive thing to try first, using values that we could later handle programmatically is even better, something like this. For example, we could create a data type called permission level that could be either guest, user, and admin. And then we could create this UI exception type. Recall this is not an instance of the exception type class, so it's just a normal value. This is just a name. And this data type has three values. It could be either a wrong input and returns the input of the user. It could also be that the user has the wrong permission and we return the permission level of the user that tried to do the action. And it could be also that the user did not log in. So we could create this sum function, for example, that takes two values of type A, that is an instance of integral for some reason, and returns an either UI exception if something goes wrong, or a value of type A if everything is well. And further down the line, we can use this extra information to do things programmatically. For example, if either returns left user did not log in, we can redirect the user to the login page. So it's not just to leave messages, it's also to take appropriate action. For this lesson, we will stick to string to keep it simple. Same as with maybe, there are also many functions already available that return either values. As you might imagine, one of those is the either equivalent of the read maybe function. We have the read either function that takes a string and returns a value of type either string A when A has to be a type that is an instance of the read type class. And if we apply this function to the same values previously, the first one returns write 57, but the second one, the wrong one, instead of returning nothing with no useful information, we get left value no parse. At least we know that the problem was that the value didn't parse. Notice how it returns the same that we will otherwise get as an exception, but this time we are getting it as a plain string, and our program never stops running. With all that, let's transform the rest of the code. The main function is almost the same. We just changed the read maybe for a read either, and instead of pattern matching for just and nothing, we pattern match for right with the correct velocity or left with a helpful message that we print. In the case that it fails with left, we recursively call main to try again. And because now we can return a message if something is wrong, the velocity function becomes more interesting. We take two either string ints and return an either string int. And in the case that both are right, we just apply save div e to both. In the case both are wrong, we can return a helpful message with the actual values to help troubleshoot the problem. Same if only distance or time are wrong. And that's pretty much it. Finally, there are ways to go from one to the other. We already saw how to go from normal values to exceptions. We just throw an exception. But what if we have an exception and we want an optional value? The easiest way to go about it is using the try function. The try function uses catch under the hood. Try takes an IO action and tries to run it. If everything goes well, it returns the final result using the write constructor. So we run the IOA action and we get the A value that it will go here. We apply write to the A value to have a value of type either EA, but because we run an IO action here, we have to wrap the result in IO again, and we get IO either EA. But if something goes wrong, catch, we capture all the exceptions of type E and return them using the left constructor. And same as before, if the raised exception is of a type different than E, it will keep propagating. So let's say we want to read a file. We are running three IO actions here. First, the post-string line asking for where's the file. Then we get the input of the user expressing the path of the file or the name of the file. It's in the same directory. And we provide the result of this action, whatever the user wrote, as an input for read file. Finally, the result of reading the file we provided as input is binded to contents. All we have to do is choose to print the contents of the file. Notice that plenty of things can go wrong in this composed action. We are interacting with the outside world 3 times. So in this case, we cannot prevent the possibility of an exception. We're interacting with the outside world, so unexpected things might happen. But using the try function, we can handle the exception under the hood and only interact with optional values, like this. In this case, the actions are the same. except that now we apply try to this massive IO action. So we are ready to catch errors of any of these three actions and transform it into an either normal value. Because we have an either value here, we have to use case to handle the left and the right cases. In the case that it's a left, we know that some error happened, so we are going to print a warning and show the error. In this case, because we are interacting with the outside world, the error is of type IO exception. And after logging this error in the console, we recursively call main to try it again, maybe with a different name file. But if everything went well, we will get a right value with the actual contents of the file, and we just print it same as before. And that's pretty much it. We learn how to handle exceptions using the exception mechanism, how to use optional values to keep our error handling within the regular execution of our program, and finally, how to move from one system to the other. To end this lecture, let's compare the two of them to see what are the trade-offs. In theory, the key difference between using exceptions and optional values is that when we use optional values, we are handling errors in the program itself. We are not stopping the execution and silently propagating the error throughout the stack. The error happens in a specific place and is part of the normal execution of the program. In practice, there are more things to take into account. For example, using optional values, the errors are evident by the types, so you know when you are dealing with them. In the case of exceptions, they are hidden from you, so you are unaware of how a function can fail by only looking at its type. Optional values are pure and such easy to predict. On the other hand, you can only catch exceptions inside impure code, which makes your program harder to predict. Optional values are also easy to use when exceptions are more complicated, but also managing multiple levels of optional values may add to the complexity of your code. It may or may not add because there are ways to hide this complexity from the developer. We will get into that in the abstraction section of the course. In the case of exceptions, the call complexity of the happy path, the path that you go through if everything goes fine, stays the same, but there's added complexity elsewhere. A bad thing about optional values is that they don't compose well with functions that take the unwrapped value, which generates a loss in modularity. It happened to us when we changed from using read to read maybe. That made it so our save div that took two integers could not work anymore, and we had to change the function to handle the cases of the maybe inputs. So it makes it a bit more verbose and harder to compose. In the case of exceptions, because they are hidden, they don't affect composability. With optional values, you can have accidental strictness, which is not unavoidable, but it becomes easy to make our functions strict. Because if you have a bunch of functions that take and return maybe values, you have to evaluate each value before going to the next function. So you are forcing the compiler to evaluate the values in a specific order, which reduces the possibilities that the compiler has to optimize the code using laziness. In the case of the exceptions, they don't affect laziness and don't affect either the compiler optimizations. And finally, and crucially, optional values cannot handle asynchronous exceptions because those happen outside our code. In the case of exceptions, we can catch asynchronous exceptions. This is a more advanced topic, but I put it there just for completeness. This is a place when exceptions is pretty much the only option. So, what should you use? Well, For now, try to use optional values, maybe either, etc., there are others, as much as possible to implement pure algorithms. Also, if a failure is expected, it's better to explicitly indicate it with an optional value. For example, the lookup function, a function that takes a value and searches inside a list of tuples for a tuple that has the same value as key and returns the second value as result. This lookup function returns a maybe because it's expected that the key we ask for might not be there. We don't know which values we are going to have there, so it's not a thing that we should assume is extremely rare. So we have to wrap the result in a maybe to indicate to the user of the function that we may return a value, but if there is no key of the value we pass, we return a nothing. If the failure is a rare this should never happen case, using an exception is usually the best choice, because something will likely never happen and it's not worth it to fill your code full of maybes or eithers. The last point is that in many cases the choice between exceptional and non-exceptional can be blurry. In those cases, you'll have to use your best judgment. Finally, a last remark is that if you feel like this is not enough, don't worry. Further along the line, you will encounter knowledge that will unlock new ways of handling errors and exceptions, giving you even more flexibility. And that's it for today. Make sure to do the homework, and I will see you in the next one.